Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss electric dipole and dipole moment, force and torque on an electric dipole, potential energy on dipole due to uniform electric field. Let's begin. Electric dipole and dipole moment. Electric dipole, when two equal and opposite point charges, equal and opposite we consider plus q and minus q, these two equal and opposite point charges are separated by a vector distance, let 2L be the distance between these two point charges, is known as electric dipole. Two point charge, one is minus q, another one is plus q, these two are separated by a vector distance, that is 2L, that is known as an electric dipole. And dipole moment, electric dipole moment of an electric dipole is a vector quantity and its magnitude is equal to the product of magnitude of either charge, either negative charge or positive charge magnitude, and the distance between the two charges, and whose direction is from negative charge to positive charge. As electric dipole moment is a vector quantity, so it has magnitude as well as direction. So its direction from negative charge to positive charge, and that one is denoted by P. Electric dipole moment. So electric dipole moment P is the product of magnitude of either charge. So the magnitude of the either charge, that is q, into the distance between the two charges, that is 2L. This is the electric dipole moment magnitude P, 2qL. But in vector form, P vector, it is electric dipole moment, it is q into 2L, and its direction from negative charge to positive charge, negative charge to positive charge, the direction of that of electric dipole moment, that is electric dipole, that is electric dipole moment. Now we studied force and torque on an electric dipole. When that electric dipole is placed in an electric field, then what happened? There are two possible scenarios. When the electric field is uniform, then what happened? And another scenario, when that electric field is non-uniform, then what happened to that of electric dipole. So first case, case 1, when that electric field is uniform electric field, let we consider an electric dipole minus q plus q that separated by a distance 2L, that placed in an uniform electric field, the uniform electric field, that is E vector. That electric dipole is placed in an uniform electric field E vector, and that making an angle theta with the direction of that uniform electric field. Let that makes the angle here, the angle between electric field and that dipole. This is the electric field, this is the direction of that dipole, that is dipole moment from negative to positive. So, the angle between electric field and dipole is theta, that angle is theta. This is the dipole moment from negative to positive. When that electric dipole is placed in a uniform electric field that experienced a torque. How? Here the force experienced by the positive q charge in that of electric field, that force will be that direction, and that amount of force, that is q into E. The force experienced by plus q in the electric field that F is equal to q into E, that is along the direction of electric field, that force direction along the direction of electric field. Again the force experienced by that negative charge on that electric field, here that is minus QE, that the direction is just the opposite of the direction of electric field. Again the force experienced by minus q in the electric field F minus QE, that is opposite to E vector. Therefore, the net force on the dipole in uniform electric field will be 0. Therefore, the net force on dipole in uniform electric field that is F total is equal to QE, force on plus Q, and force on minus Q, that is minus QE, the value will be 0. So, here when an electric dipole is placed in an uniform electric field, so the force experienced will be 0. But since the electric dipole is under the action of two equal and opposite forces that executes torque. Here, since electric dipole is under the action of two equal and opposite, or we can say unlike, parallel forces hence it gives rise to a torque on dipole. So, that dipole execute a torque. What should be the magnitude or direction of that of torque? Therefore, the torque acting on that of electric dipole is given by magnitude of either force into the perpendicular distance between the two forces, into the perpendicular distance between the two forces. So, tau is equal to magnitude of either forces, that is QE, into the perpendicular distance of the two forces. This is the perpendicular distance here, that is the perpendicular distance, let named as AM. Look here, from the triangle AMB, that angle is theta. So, sin theta is equal to AM divided by AB. Here in triangle AMB, sin theta is equal to AM divided by AB, which implies AM is equal to AB sin theta, which implies AM is equal to AB, that is the length of that of dipole, 2L sin theta, or tau is equal to QE into 2L sin theta. Therefore, 2QL into E sin theta, QL, 2L, that is the length of the dipole, into the charge, that is the dipole moment. So, here tau is equal to dipole moment P E sin theta, as P is equal to 2QL, that is the dipole moment. here in vector form tau is equal to P cross E, when an electric dipole is placed in an uniform electric field that experienced a torque, and the torque will be P cross E. P the electric dipole moment, E the electric field intensity. This is one case when that electric field is uniform, but when that electric field is non-uniform, then what happened? Case 2, non-uniform electric field. Non-uniform electric field. When an electric dipole is placed in a non-uniform electric field, then what happened? In addition to that of torque experienced, again a net translatory force on the dipole executed, because the forces acting on two ends of that dipole are not exactly equal and opposite. Okay. When that dipole, let minus q plus q is placed in a non-uniform electric field, then what happened here? It executes torque plus net translatory force, because here the force acted upon the two ends will not equal and opposite. That is why it creates net translatory force. But in case of uniform field, the net force will be 0, but here that net force creates the translatory force and with the torque also. But in uniform field, net force 0, but torque will be there. But in non-uniform case, both torque and net translatory force is created. We have to calculate these two. Let us derive the general expression for net translatory force on the dipole. For this purpose, we have to consider the variation of electric field components. How? Let we take the electric field components, are that of negative charge, at negative charge of the dipole that is Ex, Ey, Ez. These are the electric field components are the negative charge. Again at positive charge of the dipole, the electric field components are let Ex dash, Ey dash, Ez dash. These are the electric field components at positive charge and negative charge respectively. And let the coordinates of minus q, coordinates here take as let coordinates of minus q as x, y, z, and for plus q as x dash, y dash, z dash. That is the change in x as x plus delta x, y plus delta y, z plus delta z. Okay, this is the components of electric field and this is the coordinate of that of charge, that the components for electric field of plus charge, that is the coordinates of plus charge. Right here the x component of electric field at charge plus q that is Ex dash. What is Ex dash? So the x component of electric field Ex dash at plus q, which is Ex dash is equal to Ex plus the change in Ex due to change in coordinate. Ex dash at the x component of that of electric field at plus q, that is Ex plus change in Ex due to the change in coordinate. As coordinate change, accordingly the electric field also changes. So here we write Ex plus change in Ex due to the change in coordinate, that will be del Ex by del x into delta x plus del Ex by delta y del y del Ex delta z del z. This is for Ex dash. Therefore, the total force acting on dipole in x direction, therefore total force acting on dipole in x direction, that is Fx, which is q Ex dash minus q Ex. Q taking as common. Okay, first we put these values. In place of Ex dash we substitute Ex plus del Ex del x delta x plus del Ex del y delta y plus del Ex delta z minus q Ex. Q Ex cancel out, only these terms exist. So the existing terms are written q del Ex delta x del x plus del Ex delta y del y plus del Ex delta z del z. that entire term is written in the vector way as I cap del Ex by del x plus j cap del Ex del y plus k cap del Ex del z, that is dot product with I cap del x plus j cap del y plus k cap del z. There will be no such change. The dot product result of these two is that one. Here q, that entire term, is the gradient of x component of E dot that thing, the change in that length, it is delta L. Q dot delta L, that is charge into small change in that dipole, that is the dipole moment. Here we have f of x, total force along x direction f of x is equal to grad Ex dot P. Why? As we write, P is equal to Q into delta L, and the term delta L, which is known as vector length of dipole, delta L, that is the vector length of dipole. Similarly, the total force acting on dipole along y direction. Similarly, total force acting on dipole in y direction, that is f of y is equal to grad Ey dot P. And total force acting on dipole in z direction, that is Fz is equal to grad Ez dot P. Total force along x direction, total force of that of dipole along y direction, total force of that of dipole along z direction. Adding these three, we can get the total translatory force on dipole when that dipole is placed in a non-uniform electric field. Therefore, the net translatory force or total translatory force on dipole in a non-uniform electric field is F is equal to Fx I cap Fy j cap plus Fz k cap, or F is equal to grad Ex P plus grad Ey P grad Ez P, or F vector is equal to, since these are dot product, changing its way, that result will be same, grad dot P dot grad Ex P dot grad Ey, P dot grad Ez, or F is equal to, that is P dot grad into E vector. E vector x, y, z are the components of E. That is the total force acting on that of electric dipole when that electric dipole is placed in a non-uniform electric field. So, here P dot grad, that one P dot grad, which is the Px del by del x plus Py del by del y plus Pz del by del z, which is known as special differential operator, that represents special differential operator. This operator, when operates on Ex, Ey and Ez, that gives the corresponding components of force on that dipole. So, here we know that when that dipole is placed in a uniform electric field, that experienced a torque, but when that dipole is placed in a non-uniform electric field, it experiences torque with net translatory force, and net force on an electric dipole in an electric field, uniform electric field, will be 0. Now, we discuss about when that electric dipole is placed in a uniform electric field, then what should be the potential energy on it? What should be the potential energy on it? Here we take that of electric dipole of dipole moment P vector, that placed in an electric field having the electric field intensity E, which creates an angle theta, that is the angle between P and E. So, a torque is created. This is the dipole moment, this is the electric field. So, the torque tau is equal to P E sin theta, as we have already discussed. Then the work done in rotating that dipole through a small angle d theta, then work done in rotating the dipole through a small angle d theta against the torque, against torque, dW is equal to tau d theta, or dW is equal to P E sin theta d theta. Then the total work done, therefore total work done in rotating the dipole from angle theta 1 to theta 2 is given by W is equal to, that is from 0 to W integration over P e sin theta d theta from theta 1 to theta 2, or total work done W is equal to P e sin theta d theta from theta 1 to theta 2, or W is equal to P e minus cos theta from theta 1 to theta 2, or W is equal to minus P e cos theta 2 minus cos theta 1. The work done, that is rotating the dipole from the angle theta 1 to theta 2, that work done is stored in the dipole as the potential energy. So, this work done will be stored in the dipole as potential energy U. Therefore, that U is equal to W, or that potential energy U is equal to minus P e cos theta 2 minus cos theta 1. The potential energy of dipole in a uniform electric field. Here we take a special case. Special case, if the dipole initially perpendicular to electric field, if dipole is initially perpendicular to electric field, that is, here theta 1 is equal to 90 degree and theta 2 is equal to theta, initially perpendicular to that of electric field. So, theta 1 is 90 degree, theta 2 is the angle of rotation, that is theta. Therefore, the electric potential energy U is equal to minus P e cos theta minus cos 90 degree, cos 90 0, or U is equal to minus P e cos theta, P e cos theta, that results P dot E, P dot E. Potential energy is equal to the negative of dot product of electric dipole into electric field intensity when the dipole is perpendicular to that of electric field. So, with the help of this video lecture, we understand the concepts of electric dipole and dipole moment, force and torque on an electric dipole. When the electric field is uniform, then force will be 0, but torque created, that is the mathematical form of torque. And when the electric field is non-uniform, then both force and torque is created. So, the translatory force, the net translatory force is that one, that is associated with the torque also. And last, we discuss about the potential energy of dipole when that is placed in a uniform electric field. Potential energy, and treating a special case when the dipole is perpendicular to that of electric field, then what happened to that of potential energy. So, with this useful and informative notes, let me wind up this session. Thank you.